Now we will apply some of our transfer function algebra rules to reduce complex systems into simpler ones using just effective transfer functions. So in this system, we have G1 and G2, and we are going to put them in series. So let's have some input U and some output Y. And what we're looking for is Y over U. All right, so they're in series. So we know from our algebra rules how to simplify that. This is going to be the same thing as U coming in, going through a transfer function and coming out as Y. And for transfer functions in series, it's going to be the product of the two transfer functions. So we need to find G1, G2. Well, we're given G1 is 2 over s squared plus s plus 1, and G2 is s plus 5. So I can just do that multiplication. So I can distribute that 2. So I have 2s plus 10 on top, and I'll have an s squared plus s plus 1 on the bottom. And actually at this point, it's in the standard form I want. I have descending powers of s in the numerator, descending powers of s in the denominator. So this is the effective transfer function. So I could rewrite this as just one transfer function, 2s plus 10, over s squared plus s plus 1, and coming out is going to be y. So this is my complete effective transfer function for these two transfer functions G1 and G2 set in series. Let's take these same two transfer functions G1, G2, but now put them in parallel with each other. So I'll have some input U, and my ultimate output will be Y. Now this is just two transfer functions in parallel, so it's pretty simple to set up. This is going to be the same as U coming in to one effective block and coming out as Y, so we don't need those intermediary signals. And when we have transfer functions in parallel, we are going to add their values together. So this will be the same as G1 plus G2. So let's do the algebra to add G1 and G2 together. We'll have 2 over s squared plus s plus 1 plus s plus 5. All right, so we need to put the s plus 5 over a common denominator. So I'll just do s squared plus s plus 1 and s squared plus s plus 1 in the numerator. So I've multiplied it by 1 in such a way that now we have a common denominator. So this will be, and this has to be in parentheses here, 2 plus s plus 5 times s squared plus s plus 1 over their common denominator of s squared plus s plus 1. I can distribute in the numerator. I have a 2 plus, I have an s times s squared is s cubed, plus s times s is s squared, plus s, plus a 5s squared, plus a 5s, plus 5. And all of this will be over 2s squared, or just s squared, plus s plus 1. That can clean up a little bit in the numerator now. Let's see, I have an s cubed term, so I'll put that out in front first, so that's taken care of. I have an s squared, I have a 5s squared, so that will give me 6s squared. So the s squared terms are now taken care of. I have an s and a 5s, will give me 6s. And I have a 2 plus 5 will give me 7. And for the denominator, that just stays as s squared plus s plus 1. And this is G1 plus G2. So that would be my final result. That is the effective transfer function when I have G1 and G2 in parallel. Again, I want to add them together. And finally, let's look at G1 and G2 set up in a negative feedback loop. It goes through G1, then back through G2, and is fed back into that summation. So we're going to have our reference signal R, and we'll have our output Y. We are looking for Y over R. Well, for a negative feedback loop, we know what this is going to look like. We're going to have our reference signal, and then our effective transfer function is going to be g1 over 1 plus g1, g2 for a negative feedback loop, and that comes out as y. All right, so let's see what this is going to look like. Setting up the algebra, I'll have a 2 over s squared plus s plus 1 over 1 plus, and we actually already did g1, g2 before, and that came out as we're going to have 2s plus 10 over s squared plus s plus 1. All right, so this is g1 over 1 plus g1, g2. Write that again here. But it's not in the standard form we want. I don't want fractions in my numerator. I don't want a fraction in my denominator either. So what I'm going to do is multiply top and bottom by s squared plus s plus 1. So I'm able to rewrite this. Okay, so in the numerator, I have an s squared plus s plus 1 in the numerator times 2 over s squared plus s plus 1. So those are going to cancel each other out. So I will be left with a 2 right now in my numerator. In my denominator, I'll have a 1 times s squared plus s plus 1. So that's from the 1 plus, now here, the denominator and will cancel with the s squared plus s plus 1. So I'll have a 2s plus 10 left. Right, so I can add these together. I will have an s squared plus 3s plus 11 left in the denominator. And at this point, I have everything in the form I wanted. I have descending powers of s in the numerator. Well, it's just a constant 2, but it's descending powers of s in the denominator. So this is going to be effectively the transfer function. So r is going to come in. It's going to go through this effective transfer function. And it's going to come out as y. And that is g1 and g2 set up in this negative feedback loop arrangement.